I'm going to talk about the NMR, nuclear magnetic resonance. So, in short, it is known as NMR. And there are two types of NMR, that is called proton NMR and the carbon NMR. So, we can say proton NMR. In short, it shows like this, or HNMR, and another is carbon NMR. In short, it shows C13 NMR. Okay, so the basic principle of this proton NMR and carbon NMR almost everybody knows. If you don't know, like, just read some basic spectroscopic book and you will know. So here I'm going to show the application, or like how to read those proton NMR and carbon NMR to determine the structure. So before doing that, I'm going to describe some basic information to read. So the proton NMR is like a spectrum or signal. So if you see the H1 proton, so in the nucleus there is one proton. Okay, so that one proton always like spinning in a with a axis. So it form a like motion like a spin. So if you give some magnetic field, so it start spinning more. So and such way that spinning flip. So in that case, that proton spin is direction is changed. That is called Larmor frequency. So due to this Larmor frequency, it form some energy change. So like if you have the proton, so it has a ground state and it has a excited state. So that proton, like with the magnetic field, the spinning is starts so faster, so it changed its position and spin changed, and due to and then it returned back to its ground state again. So in that case, it form a like signal, so slowly decaying signal, and that signal normally convert to a spectra, like a certain signal. That signal can be converting to the peak with the Fourier transform method, FT, Fourier transform. So that signal actually normally visible in the proton NMR spectra. So this is very basic thing. If you want to know more about it, then definitely you can go basic book on the spectroscopic book, more details on that. I'm not going that details. I will discuss how to read that proton spectra and carbon spectra to determine the structure. So very first thing, we want to know, so the proton will be dancing, more dancing, it will require less magnetic field. So in the scale of the proton NMR, so it started from 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is proton NMR scale. And this scale is called ppm. Okay, so if this is close to 0, so it's called upfield. and as you go down, it's called downfield. Like downfield means like higher ppm, and upfield means like is smaller, like lower ppm. So that means downfield require less magnetic field, and upfield require more magnetic field. So this is the scale. So if any proton is shows around 1 to 3, suppose if you have a signal here, that means we can say this proton is requiring more magnetic field. But if you see any proton like a downfield, that is called downfield, more value is downfield. So if you see any signal here, so we can say this require less magnetic field. So in that case, why, like what is the reason? So in case of proton environment, electronic environment, it determine where it will show up. Okay, so any proton, if its surroundings has a electronic density, okay, so if somehow you can reduce the electron density from here, like suppose electron density is removed somehow, then this is like surrounded by electron density. Okay, more electron, so it will be like more shielded. Okay, that means shield mean like a screen. So you require more magnetic field to make it more dancing. Okay, but if electron density is reduced, then you will require less magnetic field to dance it, to make it more dancing. Okay, so more electron density, it will be like upfield, more shielded. Less electron density, it will show up downfield or less shielded. Okay, so let's see another example. So suppose a person is standing, okay, and if you give heat from the down, then it will start dancing, more dancing. Okay, like heavy dancing. So it will start dancing more. But a person, so a person, but if you make some kind of shield or screen and give heat here, so that person will not get that much heat, so ultimately it will dance less. So that means the same scenario for the a proton near to, if it has a more electron density around it, it will be like require more magnetic field to dance. So suppose a proton is connected with a carbon, and that carbon is connected with other carbon and proton. So if we consider this proton specifically, so that see, now if we consider this green proton, so that proton is connected to this carbon, so they have some electron density in between these two carbon and proton. Okay, and now consider another proton which is connected next to a chlorine, hydrogen, and another carbon, maybe like this. So now if we consider this proton, so in that case, that proton will have less electron density around it than this proton. Why? Because we can say that electron density is pulled by this chlorine. Okay, so that hydrogen will be more easier, like less screen effect. That's why we can say less shielding. That means de-shielding. Okay, de-shielded, SHIELDED, de-shielded proton. But here we can say it is more shielding or shielded proton. So we can say this is a shielded proton. Okay, so that's why this proton will show upfield. That means near to 0 to 3 or something. But this proton will show up downfield. That means near to 3 to 5 ppm. And it will be like 0 to 1.5 or something ppm. Okay, so that's the thing I'm trying to say. The electron density near to the specific proton we want to see. Okay, so it is true for every other proton too. So that's how we can say the electronic effect can change the environment in the proton NMR. Okay, so more electron cloud near proton, more shielding or screen effect. Remember that, more electron cloud near the proton, you will see more shielding or like that is screening effect. Okay, so I hope you already understand the electron effect. So the proton easily get magnetic field, show up downfield. The proton having shield show up upfield. So if you now go back to the scale, so whichever the proton has more electron density around it, so those will show up around this scale. The protons which are like less electron density around, it will show downfield. That means upper value, more de-shielded. So shielding effect and de-shielding effect, I hope you understand. So there is a couple of more things since I am talking about the shielding. So another thing is, sometimes some molecules itself are producing magnetic field. Okay, so like alkene type molecule, they are planar. Okay, so it produces some magnetic field around this molecule. So you can think of like it is making some magnetic effect through this bond, and then it is coming out this way, and then so this ethylene molecule, it produces magnetic resonance through this molecule, and when it is coming out through the plane, that induced magnet activate those protons actually. Okay, and that's why it is getting more magnet easily. So that's why they are more down shielded, de-shielded, so they will show up downfield. Okay, so normally those alkene type proton show up normally 5 to 6.5 ppm. And same case if you think for the alkyne type proton, so if you give the magnetic field, it normally go through the bond and also align with this proton. Ultimately that proton is not activated. So if those proton is in the like outside this magnetic direction, then those proton could be more activated, but now it is aligning with the same direction, so that's why they are not activated. So alkyne type proton normally is more shielded, so that's why it will show up near to 1 to 4 or something. And similarly for the alkene, so if you think for the aromatic ring, they have alternating double bond, so it has proton outside. So if you give the magnetic field through this bond, so it will go the magnetic field through the middle, and when it go out, it will activate this proton in the plane. Okay, so it will make this proton more de-shielded because of this magnetic effect. So this shielding and de-shielding effect, this effect has a name. uh, so that's why the aromatic proton always show up around 7 to 8.5 ppm, because when you put magnetic field, that magnetic field normally goes through the middle of the molecule, and then that magnetic field activate the outer side proton in the plane, because aromatic ring is a planar compound. Okay, so now let's review the scale again. If we want to see the proton scale, it is important to know, to remember. So let's do scale again. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so remember this is called upfield. Like as you go down, like ppm, like smaller ppm, upfield, like shielded. Okay, so if you write more shielded, or it's called upfield. Remember that upfield is not like upper value. Okay, upfield. And if you go down, so that is called de-shielded, downfield. Okay, now normally we can show the electron as I was discussing. So any proton, normal proton, if you have something like this, so that proton, that specific proton, this proton or this proton or this proton, will have the similar type of effect. But if you consider the similar molecule, if you consider the similar molecule like this, here is like chlorine or bromine or iodine or whatever, and another molecule like CH3 and H2. Okay, it has a double bond electron. So that nitrogen or any molecule or this like carbon with the oxygen. So any carbon next to the oxygen, so that proton will get some impact for that oxygen. Any carbon next to the nitrogen, so those proton will get impact for this nitrogen. Okay, and similarly any proton next to chlorine or bromine or iodine, those proton will get impact for that, because the electron density will be pulled by the electronegative atoms. So this is also, nitrogen is electronegative atom, so it will pull the electron density itself to itself. so that electron density will go to this, and that's why those proton will be like more de-shielded, like lower value. Okay, so now let's see the scale common to remember. We can take a new one actually. So again, if we see scale 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 ppm. Okay, so any normal proton, suppose you have CH3, CH2, something like another CH3. Okay, so this proton will show up around 0 to 2, normally around 1.5. Okay, normal aliphatic protons. Okay, so if you have any protons, like suppose you have a CH, okay, and that proton is next to a carbon, oxygen. So since this oxygen is near to these protons, so all those protons will show up around 3 to 4.5, 3 to 4.5 ppm. Okay, next to the oxygen. Not only that, next to nitrogen or next to chlorine, those are also like around 3 to 4 or 3 to 5 ppm. Okay, so any proton. So that's why I can say a proton next to a carbon connected with halogen, or a proton a proton is connected to the carbon, that carbon next to the oxygen, or a proton connected with the carbon next to the nitrogen. So all those normally show up around 3 to 5 ppm. Okay, just you can remember those, like if you see any signal there, so always look for that proton connected carbon is next to oxygen or halogen or nitrogen. So let's do some other assignment. So if you know those things, immediately you can understand the some important pieces from the proton NMR spectroscopy. So if you see something, any peak around 6.5 to 5, like 5 to 6.5 ppm, so you can say can be alkene, those can be alkene type, alkene or vinylic proton. How does it looks? So if you have double bonded carbon and that has a proton or something, so if you have something like this, like whatever, so that kind of proton will show up in the like 5 to 6.5. Okay, so any aromatic ring like benzene ring, if you have any aromatic proton like that benzene proton, so that can be substituted or non-substituted, whatever. Okay, so all those proton will show up where in this scale. So normally 7 to 8.5 ppm. Remember that aromatic peak. If you see any signal like sometimes very rare case like 6.5 to 8.5 ppm, but mostly 7. Okay, most time 7. So if you see any peak around here, so you can immediately say, okay, I have aromatic ring. Okay, so for the aromatic, that's why we can say this area is called aromatic area. Aromatic signal, aromatic proton signal. Now if you have any signal from 9 to 10, very small window, that is actually for aldehyde peak. What is aldehyde look like? So if you have carbonyl group with a proton, so that proton actually will show up there like 9 to 10 ppm. Okay, and most of the case people say above 10.5 to 13 or 14, whatever it is, so that is called carboxylic acid peak. Carboxylic acid peak. Okay, so if you now look on this scale, definitely for the normal proton, um, if we go again from normal proton, you will see this area 0 to 2. Any proton having the oxygen or nitrogen or halogen nearby, so that will be that region. Any proton is a vinylic or alkene or carbon double bond, then that proton will be like 5 to 6.5 ppm. Any proton that is like aromatic, so you will expect 7 to 8.5, that range. And any proton, aldehyde proton, that proton will show up 9 to 10. And carboxylic acid peak, it will show up from 10 11 to 13 or like 11 to like above 10. Normally that carboxylic peak is not visible. Many times people may not see that. Okay, so now let's do a practice. Suppose you have CH3, CH2 and CH3. So without considering the splitting pattern, if we say how many types of proton we have in this molecule, we have actually two different, 1, 2, and it is also 1 because it's a mirror image. So in the proton NMR you will see like peak like this. So a methyl peak, that will be very shielded, or like 0 to 1, and CH2 peak, like there is another peak. So those will be like that closer. Okay, now if you have a CH3, CH2, O, CH3, so in that case again 0, 1, 2, two, 3, 4, 5. So now if we number the proton type, this is 1, this is 2, this is 3. Okay, so number 1 type, like that is number 1. Okay, and number 2, that proton is next to oxygen, so it will show up around 3 to 4, so something like here. And number 3, that proton also next to the oxygen, so you'll see another peak, another types of peak. Now I am not showing the splitting pattern. Okay, just see the position of the peak where you will see. So for this molecule you will see this proton. Similar case, if you have any double bonded like CH, CO, CH3 and CH3, CH3. Okay, so those molecules, so it is kind of A, it is kind of B, they are different, and C and D. Okay, so now in the scale, how you are going to see that? So if it is 0 and that methyl A and B, so you will see 1 2 3 4 5 6 7. Okay, so now you are going to say A and B near to 1 to 2, because that is also next to the that carbon carbon double bond, so it will be like little bit upfilled. And D also you will see around 2, because that is next to the carbonyl group. Okay, so next to the carbonyl always show up, any proton next to the carbonyl always show up 1.8 to 2.1 ppm, just to remember, like any methyl peak or something. Okay, now the C proton, you will see the C proton around 5 to 6, because that proton is vinylic proton, because it has a double bond and that carbon is directly connected here. Okay, now let's see any aromatic ring. Like if you have a benzene ring, then how you are going to see those peaks? Suppose here chlorine, bromine, here, suppose NH2. So here A, B, C. So now if you see, remember that you will see the aromatic peak is around 7 to 8 ppm, very normal case. Okay, so now you can see H, like A as a singlet A, and B as a doublet, and C also as a doublet, because they will see each other. I will explain more splitting pattern, don't worry. So these are the like pattern you will see in the proton NMR. Now I'm going to show the splitting and the multiplicity. Okay, so let's see how we are going to explain the splitting and the multiplicity. So the rule is n+1 rule. Okay, for the proton NMR, n is the number of neighboring proton. Neighboring proton, what is neighboring proton? Neighboring proton, that is 3 bond away proton. Like suppose you have a proton here, and chlorine here, bromine here, and this is a proton, and this is a carbon, and this is carbon. Now if we consider this proton, from this, like count how many bond is away. 1, okay, 2, 3. So that is a neighbor. Neighbor proton. Okay, so 3 bond away, 1, 2, 3. So that n+1 will be like how many neighboring proton, like 3 bond away. So if you consider, suppose if I want to write this methyl as a different way, like suppose if I consider this way. Now if you count from this proton, how many bond from this proton, so you will see, suppose 1, 2, 3, 4. So that's why it cannot be the neighbor. Okay, but if you go like 3 bond from this proton to this proton, so you can count 1 2 3, like three bonds, so that's why it is neighbor. Okay, now for a neighboring proton, your rule is n plus 1, like number of neighboring proton will added up with 1. Suppose in this molecule, for suppose if we say A and B, so for the A proton, okay, how many neighbor proton is there? 1. So n value is 1 plus the rules 1, so you will get 2. That 2 means that is called doublet. So that proton will be splitted by like this, that is called doublet. Okay, now what if we have a proton actually has 2 neighbor? So now if we consider this proton as a, so that A has 1 2 3, so 1 neighbor, and that A has 1 2 3, that is another neighbor. So for the A proton here, again n plus 1 rule. So for the A proton, it has 2 neighbor plus 1, so you will see 3 is called triplet. So that means A proton will show up like a triplet signal. Okay, that is called multiplicity. So similar case, if any, like now if you think that A proton has another proton here, suppose another proton here, and that proton also from the A, you will count 1 2 3 bond away, so there is another neighbor. Okay, so now for this molecule, for A proton, how many neighbor proton is there? 3. So n plus 1 rule, so 3 plus 1, it will be 4. So 4 is called quartet. How it looks like? Quartet will show up as a signal like this, or maybe I can draw again. So this is a quartet. So when there is no neighboring proton, so if you replace all those proton with something else, suppose if we replace those like chlorine, another chlorine, and another chlorine, so ultimately that A proton doesn't have any neighbor. So in that case, no neighbor, so n plus 1, so n value is 0 plus 1, so 1. That 1 is called like singlet. Okay, so now you know that if it is singlet, so it is like multiplicity is 1. If it is doublet, multiplicity is 2. So singlet is like this and doublet is like this. If it is like triplet, so it will show like this. If it is quartet, multiplicity will be 4, that means it will show like this. Similar case, if it is pentet, multiplicity 5, so the peak will be 5. 1 2 3 4 5. Okay, and next one is sextet, multiplicity 6. 1 2 3 4 5 6. Okay, septet, multiplicity 7. 1 2 3 4 5 6 7. Okay, and same case like octet, multiplicity 8. nonate, multiplicity 9. So normally after quartet, in very rare cases, people mentioned as a pentate, sextate, or septate. In many cases, those are termed as multiplet. What is it called? Multiplet. So in short, it shows as a M, multiplet. Okay. So Proton NMR, in some cases, people show BS, like broad singlet. In cases broad singlet, many cases people see broad singlet. If you see multiplet, so M, multiplet. Okay. And most cases you will see doublet, some cases doublet of doublet, some cases doublet of triplet. In some cases you see triplet, in some cases you see triplet of doublet, in some cases you see triplet of doublet, TD, same thing, and triplet of triplet. Okay. What is doublet of doublet? So if you see a doublet again is splitted by another doublet, so it is called doublet of doublet. Okay. And doublet of triplet, so this is called doublet of triplet. Okay. Triplet of doublet, that is rare, but it is possible. This is called triplet of doublet. Okay. So I hope now you understand the splitting pattern and multiplicity, and also n+1 rule. So remember that n+1. So n is the number of neighboring proton. Number of neighboring proton. Okay. Next, we will talk more about little more details, some more techniques to get ready for the structure elucidation. Till now, stay fine, and thank you for watching my video. Bye today.